Okay, so today we are going to solve some questions based upon the theory that we discussed on yesterday, right? So let us see this first question. In a region of space with volume 0.2 meter cube, the electric potential is found to be 5 volt throughout. The magnitude of electric field in this region is option A is 0, option B is 0.5 Newton per coulomb, option C 1 Newton per coulomb, and option D 5 newtons per coulomb. Can you guess? 0. Okay, it's 0. It's correct. Why? How do we define the electric field? Electric field is electric field is minus of gradient of electric potential with respect to distance, right? So if we consider, let's suppose one dimensional case. So electric field is minus of derivative of potential with respect to the position. Okay, so that is change in potential with respect to change in position. But the electric potential here is 5 volt throughout. That means it is not changing, and that means because it's not changing, so its derivative with respect to position will be 0. Okay, so electric field is 0. Two metal spheres, one of radius r and other of radius 2r respectively, have the same surface charge density sigma. They are brought in contact and separated. What will be the new surface charge densities on them? This is the question. So you have two metal spheres and they have same surface charge density sigma. Okay, but the radius of first one is r and the radius of the other one is 2r. So they are brought in contact. They are brought in contact and separated. Right? They are brought in contact. Okay, so radius of this sphere is r. Radius of this sphere is 2r. This is r. This is 2r. So what will happen now when they are brought in contact? There will be some transfer of charge, right? From where to where? Charge will move from higher potential to lower potential, right? It will move in direction of the electric field. Till what time will it keep on moving? Till the time the potential on both these spheres become equal. Okay, so we can say it will keep on moving till the time the potentials become equal, right? So now, how much is charge on first sphere? Okay, how much is charge on first sphere? We can find out. It will be what? Q1 is equal to sigma multiplied by surface area of first sphere, and Q2 is equal to sigma multiplied by surface area of second sphere, right? So now see what will happen. Potential on the first one is equal to potential on second one. So how much is potential? So it is 1 upon 4 pi epsilon naught multiplied by Q by R. So it is Q1 divided by R1 we can say, and it is equal to 1 upon 4 pi epsilon naught multiplied by Q2 by R2. And how much is R2? R2 is equal to 2R. Okay, so this thing gets cancelled. Okay, 1 upon 4 pi epsilon naught and 1 upon 4 pi epsilon naught gets cancelled, right? And then see, this thing can be written as, now Q1 is equal to, we can say sigma 1 multiplied by 4 pi R1 square or R square. Okay, and we have R in denominator, and this thing can be written as Q2 is sigma multiplied by 4 pi R2 square, which is 2R square, right? So 4 pi gets cancelled once again. Okay, and then we have sigma 1 multiplied by r on this side, this is sigma 2. Sigma 1 multiplied by r on this side, it's equal to sigma 2 multiplied by what? This is 2r square divided by 2r. So it will be 2r, 2 times r. Now r and r gets cancelled out. So we get sigma 1 is equal to 2 times sigma 2. Okay. So this should be the answer. Okay. Yeah. Sigma 1 equals to 2 times of sigma 2. This is what we get, right? Question is, what is the surface charge density in terms of the original surface charge densities? This is the question. Okay. So that's what we have to find out. So let me add a page here. Okay. So original surface charge density. Okay. So initially there was some charge Q1 and Q2. So Q1 is equal to, we can say, sigma multiplied by 4 pi r1 square, and Q2 is equal to sigma multiplied by 4 pi 2r square, right? Now what can we say using this thing? So sigma 1 is equal to 2 times of sigma 2. Sorry, yeah, sigma 1 is equal to 2 times of sigma 2. This is what we get. Okay. So initially we have uh, two surface charge densities are equal. Okay. So Q1 is equal to sigma multiplied by 4 pi r1 square, and Q2 is equal to what? Initial values of Q1 and Q2. They are sigma multiplied by 4 pi r1 square and sigma multiplied by 4 pi r2 square, which is 2r square. But if you add up the total charge, so the total charge will be equal to what? You can say it is sigma multiplied by 4 pi r square plus sigma multiplied by 4 pi into 2r square, which will be 4r square, right? So this is sigma multiplied by 4 pi r square, or sigma times 4 pi, you can take common, r square plus 2r square. So this will be 5r square. Okay, this will be r square plus 4r square, that is 5r square. This is the total charge. Okay, this is total charge. Now see, there is redistribution of charge. There is redistribution of charge, but the total charge will remain constant, right? Total charge will remain constant. So we can say, now see here, new charge. Okay, new charge is what? Let's call it Q1 dash and Q2 dash. Okay, so new charge is Q1 dash and Q2 dash. So how much would be Q1 dash and Q2 dash? So Q1 dash will be equal to what? I can say Q1 dash is equal to sigma multiplied by sigma 1 multiplied by 4 pi r1 square, and Q2 dash is sigma 2 multiplied by 4 pi r2 square. Okay, so I can say Q1 dash plus Q2 dash is equal to sigma 1 multiplied by 4 pi r square plus Q2 dash is equal to sigma 2 multiplied by 4 pi multiplied by 2r square. Okay, this is getting little bit lengthy, but we'll come to the answer quickly now. Okay, so then what is sigma 2? What is sigma 1? It is 2 times of sigma 2. We can substitute that. This is 2 times of sigma 2. Okay, so 2 times of sigma 2 multiplied by 4 pi r square plus sigma 2 multiplied by 4 pi multiplied by 4r square. So this will give us what? This will give us 2 times of sigma 2 plus 4 times of sigma 2. right? So it gives us 6 times of sigma 2 multiplied by 4 pi r square, and that is equal to, we can say, this thing. This is the total charge. Total charge will remain constant. Okay, so we can equate it to this thing. It is sigma, the original surface charge density, multiplied by, or we can take 5. Okay, we can write 5 times sigma multiplied by 4 pi r square is equal to this thing. So 4 pi r square and 4 pi r square will get cancelled out. Okay, so we get sigma 2 in terms of sigma. So sigma 2 is equal to 5 times of sigma divided by 6. So is this what we want? What will be the new surface charge densities? Okay, we found sigma 2, and what will be sigma 1? It is 2 times of sigma 2. So it is 2 times of sigma 2. So that means sigma 1 is 10 times of sigma divided by 6. Okay, or we can say 5 times of sigma divided by 3, right? 5 times of sigma divided by 3. So this is the answer. So it is option, so option D is the answer. All right. So see, we have two spheres and they are connected to each other. Okay. So charge will get transferred from one sphere to another sphere till the time the potentials on both these spheres become equal. Okay. Till the time there is no potential difference. Because if there is potential difference, that means there will be electric field. If there is electric field, that means there will be force. Right. So V1 will be equal to V2 ultimately. Right. So we want to find out the surface charge densities. Initial surface charge densities are sigma. So using this, we can find out initial charges. Okay. So initial surface charge density is sigma. Q1 is equal to sigma multiplied by 4 pi r square, and Q2 is equal to sigma multiplied by 4 pi 2r square. Okay. So charge is equal to surface charge density multiplied by area. After that, what will happen? So finally, potential on one will be equal to potential on the second one. Okay, potential on first sphere will be equal to potential on second sphere. So we can use this formula for potential, 1 upon 4 pi epsilon naught q upon r. But what we can do is, we know that the electric field due to a charged sphere on the surface of sphere, it is given by this formula. So electric field is given by sigma upon epsilon naught. Right? Yes, no? Okay. So we can relate electric field and potential for a sphere, and for this kind of problems we can use this formula. See, so V is equal to, for a sphere, 1 upon 4 pi epsilon naught multiplied by q upon r. So now how can you make adjust the electric field on right hand side, the formula for electric field? So it is 1 upon 4 pi epsilon naught q upon r square, right? It is q upon r square. That means I have to multiply in denominator by r. Okay, so I will do this. I will multiply by r in the numerator and denominator. So this is my electric field. So I can say V is equal to what? It is E multiplied by r, or it is sigma upon epsilon naught. Okay, electric field is sigma divided by epsilon naught, and V is equal to sigma upon epsilon naught multiplied by r. Okay, so this will, okay, this formula we can use for spheres only. Okay, so now I can say V1 is equal to V2. That means the sigma dash, okay, the surface charge density will change. So sigma 1 dash, or we can call it sigma 1 also, because initially the surface charge density is equal. So sigma 1 dash upon epsilon naught multiplied by r is equal to sigma 2 dash divided by epsilon naught multiplied by what? What is radius of second sphere? It is 2r. Okay. Then this r and r gets cancelled, epsilon naught gets cancelled. So we get sigma 1 dash is equal to 2 times sigma 2 dash. Okay, quite quickly. And after that, we can find out the net charge. See, there is redistribution of charge, but net charge remains constant. Okay, so net charge, final net charge, we can say on first sphere, q dash is equal to sigma 1 dash multiplied by its area, which is 4 pi r square. And final net charge on the second one is sigma 2 dash multiplied by 4 pi 2r square, right? So charge remains constant. So q1 plus q2 is equal to q1 dash plus q2 dash. Okay. So therefore, what we can do is sigma 1, which is sigma in first case, multiplied by 4 pi r square plus sigma multiplied by 4 pi 2r square is equal to, here it is sigma 1 dash multiplied by 4 pi r square plus sigma 2 dash multiplied by 4 pi 2r square. So here we can do one more thing. So we can cancel out 4 pi r square, okay, which we didn't do earlier. So we can cancel out 4 pi r square, 4 pi r square from everywhere. So what do we get? So if we cancel out 4 pi r square, here you have 2 times of r square. So we'll get factor of 4 from here. So it is sigma plus 4 sigma, right? So which is 5 sigma, 5 sigmas is equal to, on the other side, here also we'll get, okay, here we'll get sigma 1 dash I'm sorry plus 4 times of sigma 2 dash, okay, and sigma 1 dash is equal to 2 times of sigma 2 dash, right? So that we can substitute. So what do we get? We get 6 times of sigma 2 dash is equal to 5 times of, not 6, sigma, and therefore sigma 2 dash is equal to 5 by 6 sigma, okay, and sigma 1 dash is 2 times of sigma 2 dash, so it is 5 by 3 times of sigma, right? So it is option D. So let's see this one. A hollow metallic sphere of a radius 10 centimeter is charged such that potential of its surface is 80 volts. The potential at the center of the sphere would be. Tell me, you can solve 10 like this. Okay. So 80 volts. You have a sphere. So potential due to a spherical shell, okay, or a hollow sphere is equal at all points inside the sphere, and it is equal to potential on the surface, right? Potential is same. So how can you say that potential is same? Because electric field is zero. Okay. So if you take this point and this point, now electric field at this point, any internal point is zero. That means the potential difference between these 2 points would be zero. Potential difference is not zero. Then you will get some electric field given by this formula, right? Electric field is change in potential with respect to the distance. Okay. So you have some distance. Then if potential at this and this point is not equal, if it is different, you will get some electric field, right? All right, let us see next problem. The diagrams below show regions of equipotentials. So these are some equipotentials, okay, of various shapes, how much are the potentials? 10 volt, 20 volt, 30 volt, 40 volt. Here also it is 10, 20, 30, 40. 10, 20, 30, 40, right? So, okay. A positive charge is moved from A to B in each diagram. Okay, each diagram. So, option A, in all the four cases, the work done is same. Option B, minimum work is required to move Q in figure 1. Option C, maximum work is required to move Q in figure 2. Option D, maximum work is required to move Q in figure 3. Tell me, does the work done depend on the shape of equipotential surface? It doesn't depend. Okay, work done is just equal to, so you are moving it from A to B, so final potential minus initial potential multiplied by charge. If in all four cases final and initial potentials are equal, that means same work will happen. Okay, there will be same work done in all four cases, right? If potential in volts in a region is expressed as V function of xyz equal to 6xy minus y plus 2yz, the electric field in Newton per coulomb at 0.110 is. So, if there is question like this, we must solve it, right? So, electric field is given by what? So, now I am writing it, you will directly solve. Okay, you need not write the formula. So, E bar is equal to minus of I cap multiplied by dou V by dou X plus J cap multiplied by dou V by dou Y plus K cap multiplied by dou V by dou Z. Okay, negative of gradient of potential with respect to XYZ. Okay, negative of gradient of potential, right? So it is equal to minus of I cap multiplied by derivative of V with respect to X. And what is V? V is 6xy minus y plus 2yz. Okay, so while taking this derivative is partial derivative of this thing with respect to x. So because it's partial derivative, we treat, if we are taking derivative with respect to x, we'll treat the other two variables as a constant. Okay, so y is constant, z is constant. These two terms are constant. That means how much would be this derivative? The 6y, we can take it outside because it's a constant. Then dx by dx is 1. So this derivative is just 6y. Okay, so this is first one. Plus you have j cap multiplied by same thing, dou by dou y of 6xy minus y plus 2yz. So there is y in all the terms. Okay, plus 2yz. And plus you have k cap multiplied by, okay, dou by dou z 6xy minus y plus 2yz. So there is z in just last term. Okay, so this is equal to minus 6 times I cap plus you have derivative of this will give you 6x, sorry, minus 6xy minus 6y. Okay, because y is a constant. Y is a constant, right? So minus 6y into I cap plus you have derivative of this with respect to y. So you will treat x as a constant, you will take it outside. 6x multiplied by j cap, but there is more, right? So minus derivative of y with respect to y is 1. So minus 1 plus, here you have 2yz, so you will take 2z outside. Derivative of y with respect to y is 1. So this is 2z. So 2z multiplied by j cap. And here you will take 2y outside. So derivative of this thing and this thing is 0 because they are constant. Okay, with respect to z. So 2y you will take outside. So it is 2y times derivative of z with respect to z is 1 Okay, so 2I times k cap. Okay, so this is the electric field. Now you are given with uh, this point. Okay, you want to find out the electric field at this point. So it is what? So just substitute this point. So x is 1, y is 1, and z is 0. So x is 1, so it is minus of 6 times I, plus here you have 6 minus 1, okay, plus 2z. So z is 0, okay, times j, and then you have 2 times y. So it's 2 because y is equal to 1, 2 times k cap. So this is the answer. It is minus of 6i plus 5j plus 2k. Yeah, option D. Minus of 6i plus 5j plus 2k. Okay, option D. Right. So see, you might think that this also took lot of time. It will not take. Okay, if you just practice this kind of a question, it will not take lot of time. Okay, so you don't have to write down this thing. Then again, here also you don't need to write down the complete potential. Okay, complete function for potential. Just take derivatives. Okay, just take derivatives in your mind and write down. I mean, just write down this step directly. Okay. All right. So see, this kind of problems are repeated many times. Okay, so this one. In a region, the potential is represented by V of xyz is equal to this thing, where V is in volts, xyz are in meters. The electric force experienced by a charge of 2 coulomb situated at point 111 is. So once again, now this is quite laborious. We'll have to do the same thing. Okay. So what is electric field? It is minus of gradient of potential with respect to distance. Okay, I'm saying potential gradient of, right. So gradient is always taken with respect to position only. Okay. So what is the electric field? It is negative of gradient of potential. Okay. So electric field is minus of gradient of potential. So del V bar, we can write it like this. Sorry, minus of del bar acting on V, and that is equal to minus of del by del x of V into I cap. So 6x minus 8xy minus 8y plus 6yz. Try to calculate in your head. Okay, del by del y of same thing, 6x minus 8xy minus 8y plus 6yz times j cap, and del by del z of 6x minus 8xy minus 8y plus 6yz times k cap. Okay, so this is derivative with respect to x. There is no x in these two terms, so it is 6 minus 8y. Okay, minus of 6 minus 8y times I cap. Okay, plus there is no y in this term. Okay, so 8x minus 8x minus 8 plus 6z minus 8x minus 8 plus 6z times j cap, and plus okay, no z in these three terms, so it is just 6y times k cap. Okay, yeah, this is also option D. Okay, let's check. So now you have to substitute the point 111. Okay, so it's 1, 6 minus 8. So this is good. Okay, E bar is equal to minus of 6 minus 8 is minus 2. So minus 2 I cap minus 8 Okay, plus minus 8, minus 8, minus 16, minus 16 plus 6 is minus 10. So minus 10 j cap and plus you have 6 k cap, right? So this is the electric field. We want force acting on charge of 2 coulomb. So F is equal to F bar is equal to E bar multiplied by E into Q. So that will be 2 times of this. Okay. And we want magnitude of it. Okay, so I will just make some space here itself. Right. So this is equal to what? F bar is equal to 4 I cap plus 20 j cap plus 12 k cap. And you want its magnitude, so it is square root of 4 square plus 20 square plus 12 square. Okay, so that is 16 plus 400 plus 144. What is that? So 16, so it is 460, square root of 460, square root of 460. Okay, so is it divisible by 16? Square root of 460. What I can see is it's divisible by 4, right? So if you divide by 4, it will give you 1115. Okay, it is 2 times square root of 115, 115, right? And 115 is it is 115. Have I done some mistake somewhere? 115 is divisible by 5. Okay, so if you divide by 5, it is 20, 23. Oh, sorry. This is 560, no? Okay. Now this is divisible by 8. It will be 70. Right. It is divisible by 16. So, okay. So 16 times 35. So it is 4 root 35. This is the answer. Option D. Right. Okay. Now, so let us see next question. A, B, C are 3 points in uniform electric field. The electric potential is A maximum at C, B same at all the 3 points A, B and C maximum at A and D maximum at B. Tell me. We had studied this yesterday. Electric field lines flow from higher potential to lower potential. Now tell me. Option D. Right. It's maximum at B. Okay, good. Next question. The electric potential V at any point xyz is given by this thing. The electric field at 112 in voltmeter is. So this is divisible. Sorry, this one is only function of x, right? If you take its derivative with respect to y and z, you will get 0. Okay, so it is just 8x, 8x and put x equal to 1. So it is 8 along negative x-axis. This should be the answer. Option A. Yes, no? Do I need to solve? Preeti? Okay, good. So it's option A. Okay. Again, similar question. So yeah, you can try this afterwards. Okay, we just have to do same thing, right? So I will skip this and we'll see next question. But uh, you should notice how many times the same kind of question is asked. Okay, they just have to change the function. They just have to change v. That's it. Okay, and it becomes new question. There's nothing new, right? Let us see next question. A charge q2 is at the center of circular path with radius r. Work done in carrying a charge q1 once around this equipotential path would be. So they said that it's equipotential. Okay, it is mentioned in the problem itself. So there is charge q2 here. Sorry, there is charge q2 at the center, and you move some charge q1 once round this complete path. Okay, from here to here. How much would be the work done? Okay, so work done is 0. First thing is, this is an equipotential surface. No work is done to move a charge on an equipotential surface. Okay, and second thing is, you are taking this charge, moving it, and okay, you are moving this charge and once round. That means will come back to the same position. You are taking it back to the same position. So no displacement, no work done, right? Option C. An electric dipole of dipole moment P is aligned parallel to uniform electric field E. The energy required to rotate the dipole by 90 degrees is. This is the question. So the dipole is parallel to the uniform electric. Okay, initially it's parallel. So theta 1 is 0, right? Theta 2 is 90 degrees. So what is the energy required? What is energy required? Delta U. Delta U is equal to minus P cos of theta 2 minus cos of theta 1. This is our formula, right? Work done to rotate a dipole from theta 1 to theta 2 is minus P cos of theta 2 minus cos theta 1. Okay, so this is equal to minus PE cos of theta 2. What is cos of 90 degrees? It's 0. Minus cos of 0. Cos 0 is 1. So this is 0 minus minus plus. So we get P times E. This is the answer. Option B. Right? Actually, we don't even need to solve this. Okay, first thing cannot be infinity. Okay, just look at the options. The options are very strange. Other options. P square E. So we know when we rotate a dipole, in the formula, we have P times E, right? So this option, they are dimensionally wrong. Okay, it will be something multiplied by P. Okay, so this one and this one are dimensionally wrong. This one, it cannot be infinity, right? You are just rotating a dipole. Work done cannot be infinity. Okay, so these three are okay. These three are uh they are not possible, right? So only possible answer is this one. Okay. So you don't even have to solve this. Just merely just looking at the options, you should be able to guess that this is dimensionally it's not possible. It will be P multiplied by something. Okay, it cannot be P square. It cannot be PE multiplied by another E. Okay, so this is not possible dimensionally. Cannot be infinity. Okay, so what is left? This option only. Got it? Yes, no? Okay. So yeah, but this will come by practice. Okay, it will come by practice. All right, next question. An electric dipole of moment P is placed in electric field of intensity E. The dipole acquires a position such that the axis of dipole makes an angle theta with the direction of field. Okay, assuming that the potential energy of dipole is zero when theta is equal to 90 degrees, we assume this thing. Torque and the potential energy of the dipole will respectively be. So they are asking for formulae only. Okay, so what is torque? P sine theta. And what is potential energy? Minus P cos theta. Right? So it's option A. Okay, this one is simplest if we remember the formulae. Okay. Next question. An electric dipole of moment P bar is lying along uniform electric field E bar. The work done in rotating the dipole by 90 degrees is. Okay, so we just solved this, right? So this is repeated. So from 0 to 90 degrees, how much is the work done? P. Okay, this question, right? All right, next question. An electric dipole has magnitude of its charge as Q and its dipole moment is P. It is placed in uniform electric field E. If the dipole moment is along the direction of field, force on it and its potential energy are respectively. Okay, so how much is the force? Dipole in uniform electric field. Force will be zero, right? Force will be zero, and since it is in direction of the field, the potential will be minimum. Okay, potential energy will be minimum. So option C is the answer. Okay. Or I mean, if you don't remember this, you can solve for potential energy also. Minus of P cos of theta. So what is maximum value of cos theta? It's 1. When is it maximum? When theta is equal to 0, right? So put it here. So theta is 0, cos 0 is 1, but then this thing becomes maximum, but the potential energy becomes minimum because it is with negative sign. So potential energy is minimum when theta is equal to 0 and it is maximum when theta is equal to 180 degrees, right? Because for 180 this will be minus 1. Cos of 180 is minus 1 and then this will become positive. Okay, so u at 0 is equal to minus P and u at 180, that's pi, it's equal to P. So this is minimum and this one is maximum. Okay. Anyways, next question. There is an electric field E in x direction. If the work done on moving charge of 0.2 coulomb through a distance of 2 meter along a line making an angle 60 degree with x-axis is 4 joule, then what is the value of electric field? Okay, there is electric field in x direction. Okay, there is electric field in x direction. So suppose this is the electric field. Okay, This is E bar. And you move a charge through a distance of 2 meter. So charge is moved like this at an angle 60 degrees. Okay. So this distance is suppose 2 meters. This is theta. So how much will be the work done? We know work done is equal to F bar dot S bar. So it is F multiplied by S multiplied by cos of theta. And what is force? It is Q times E multiplied by S multiplied by cos of 60. What is cos 60? It's 1 by 2. And work done is 4 joules. Okay. So take that 2 on other side. So 8 is equal to Q times E multiplied by S. And we want E. So let's take QS on other side. So E is equal to 8 divided by Q times S. So that is 8 divided by 2 coulombs, right? And okay, what is displacement? Okay, it's 0.2 coulombs. Sorry, not 2 coulombs. 0.2 multiplied by 2. So this is zero point 0.4. So 8 upon 0.4, or you can say 80 divided by 4. So that's 20. Option B, right? An electric dipole moment of, sorry, an electric dipole of moment P is placed in the position of stable equilibrium in uniform electric field of intensity E. This is rotated through an angle of theta from initial position. The potential energy of the electric dipole in the final position is. So what will be stable equilibrium? So stable equilibrium is when it is directed in direction of the electric field. Okay. So this dipole is directed in direction of electric field. Okay, recall what is stable equilibrium from mechanics. Okay, let's suppose we have this pebble inside this inside this jar, we can say, or a container like this. Okay, if you displace it a little bit, what happens? It comes back to the same position. Okay, if you consider a small ball inside this kind of a container, if you displace it a little bit, it comes back to the same position. Okay, and why is it at equilibrium? Because net force acting on it is zero. Now you can consider a surface like this. The ball is kept here. So right now also the net force acting on it is zero. But if you displace it a little bit towards left, towards right, what will happen? It will slide down. It will not come back to the same position. So this is also in equilibrium. This one is also in equilibrium. But this is stable equilibrium. This is unstable equilibrium. Right? So now see the dipole, if it is oriented like this in direction of the electric field. Okay, dipole, this is minus q, this is plus q. If it is oriented like this, then if you displace it, meaning if you rotate it a little bit, it will again come back to this position. Okay, so this is true for all kinds of systems. They try to minimize their potential energies. Okay, they try to minimize the potential energy. So if you think of this example, what is the minimum of potential energy? It is this point. If you move it here, again it will come back to the same point. If you displace this one, this is at, okay, highest position. That means its potential energy is maximum. If you displace it, it will fall. Okay, so its potential energy will become minimum, right? So what is minimum of potential energy for a dipole in external electric field? It is this position. It is along the electric field. Okay, so this is known as stable equilibrium. And what is unstable equilibrium? So if you keep dipole like this, okay, plus q minus q, still there is no force acting on it, no torque acting on it, okay. But if you rotate it a little bit, it will, then there will be torque due to the electric field, which will align it in the direction of electric field, right? So okay, in this case dipole moment is like this. Okay, in this case dipole moment is opposite to the electric field. Okay, so this is stable equilibrium, this is unstable equilibrium. Got it? Yes, no? Okay. And now you rotate it through an angle theta. So how much would be the work done? This is the question. So we know work done is minus PE cos of theta 1 minus cos, cos of theta 2 minus cos of, is it minus PE cos of theta 2, theta 1 or theta 2? Sorry. Theta 1 minus theta 2, right? Work done is equal to minus PE cos of theta 1, cos theta 2 minus cos of theta 1. Okay. So initially it is along uh, the electric field. That means theta 1 is equal to 0 and theta 2 is equal to theta. So it is work done is equal to what? Minus PE multiplied by cos of theta minus cos of theta 1 is 1. Okay. Or you can say it is PE 1 minus cos theta. So option B is the answer. Right? Yes, no? Sorry. Next question. Some charge is being given to a conductor, then its potential is maximum at surface, maximum at center, remains same throughout the conductor, maximum somewhere between the surface and center. Okay. So some charge is given to the conductor, not being given. So if charge is being given, then potential will keep on increasing, right? So charge is given to the conductor. We know what will happen. The potential throughout will be equal. Okay, potential throughout the conductor is equal, remains same throughout the conductor. Okay, so let me explain this. Actually, language of this question is not correct. Okay, it doesn't remain same, it will be equal in all parts. Okay, so see, this is your conductor. You give some charge to it. You gave some charge. Then if you say it's being given, so you keep on giving the charge. Suppose now charge delta q is given, added. So what will happen when you give charge q? It gets uniformly distributed throughout the conductor. Why? Okay. See, this is a conductor, so charges can flow. Okay, charges can flow. You give some charge, it can flow through the conductor. But when will they flow and when will they cease to flow? So if potential, if there is some potential difference, then the charges will flow and they will keep on flowing till the time potential difference becomes zero. Okay, on all parts of the conductor. Okay, so what will happen if you give some charge? There will be repulsion. Okay, you are giving positive charge, there will be repulsion between these positive charges. So till what time these charges will repel each other? Till the time they settle at a particular distance when the force between them is 0. Okay, then we say the equilibrium is established. So when force is 0, that means electric field is 0, and if electric field is 0, that means there is no potential difference. Okay, so potential will be constant. But if you add some charge, what will happen? Potential will increase, right? Because what is potential? So if you think just out, potential at just outside point, sigma divided by epsilon naught. So if you give charge, surface charge density will increase, right? So potential doesn't remain constant, it will keep on increasing, but it will be equal uh, at all parts of the conductor. Got it? Let's see next question. So n identical, I'm sorry, n identical mercury droplets charged to same potential V coalesce to form a single bigger drop. The potential of the new drop will be. This is the question. So you have n mercury droplets and they are charged to same potential coalesce to form a single bigger drop. The potential of new drop will be. So what will happen here? You have this mercury droplet, suppose. Okay. So potential due to all of them will be, you can say it's 1 upon 4 pi epsilon naught multiplied by q upon small r. Okay, this is potential due to one such small droplet. Now, if you join them all, what will happen? Okay, so sorry, if you combine them all, not join, n such droplets, what will happen now? So the new drop that you are getting, it will have charge equal to, let's suppose, capital Q. So capital Q will be equal to what? It will be n times of, this is small n, right? N times of small q. Okay, total charge on bigger drop that you are getting due to the n drops being coalesced. Okay, n drops combined. The total charge will be equal to small n times q. Okay, charge on n multiplied by charge on each drop. Now, what will be the potential now? So let's call it V dash. It will be equal to 1 upon 4 pi epsilon naught multiplied by this capital Q divided by R. So the new drop that you get, its radius is suppose capital R. Okay. So now what will be V dash in terms of V? This is the question. So for that, we need to find out this R in terms of small r. Okay. Right. So if n drops combine, what happens? I can say volume of the bigger drop. Okay. Volume of, again, volume of big drop is equal to n times volume of small drops. Okay, so that is 4 by 3 pi r cube is equal to n times 4 by 3 pi r cube, sorry, pi multiplied by small r cube. So 4 by 3 pi and 4 by 3 pi will get cancelled. R cube is equal to small n times small r cube. So that means r is equal to, we have to take cube root on both sides, n raised to 1/3 multiplied by small r. So we can substitute that here. So we get V dash is equal to 1 upon 4 pi epsilon naught multiplied by Q is equal to n times small q. R is equal to what? N raised to 1/3 multiplied by small r. So you have n raised to 1 divided by n raised to 1 by 3. It is n raised to 2 by 3. Right. So it is n raised to 2 by 3 times the remaining remaining thing is it's 1 upon 4 pi epsilon naught q by r, that's potential due to small drop. So it is n raised to 2/3 of potential due to small drop. So it's option D. Got it? Sorry. Okay. So this was the last question. Okay. I added this when we started the class. Okay. So I thought it's a good question and it should not be missed. So there will be similar kind of question in surface tension, and there it is repeated many times.